Let's consider a particular example of a mass spectrometer, shown here on the right. We're going to calculate the mass of a singly ionized positive particle, that would be this particle right here, that travels through the velocity selector section, undeviated, and then curves around into a circular path through the mass spectrometer to strike the detector array at this point P, which is 0.8 meters left of the hole. So that's this distance here. That distance is 0.8 meters. We're given the values of the magnetic field in the input velocity selector region, as well as the magnetic field here for the region that produces the curved path. And we also know the electric field. From before, we have the equation for the radius of curvature of a particle traveling through a magnetic field with a given velocity, if we know its mass and we know its charge. In this case, we are trying to solve for the mass, so we're going to rewrite this equation to solve for m in terms of the radius of curvature, the charge, the velocity of the particle, and the magnetic field, right? And then we also have this equation that tells us what speed of particle will make it through the velocity selector region, undeviated, so that it actually passes through this little opening. All right, so let's go ahead and tackle that problem. Again, our goal here is to calculate for the mass. So we'll take the equation we have for the radius of curvature of the trajectory, and we'll rearrange it to solve for the mass. We'll have mass is equal to r times the magnitude of q times the magnitude of the magnetic field over the magnitude of the velocity. We were given the magnitude of the magnetic field in this region, right? We have a value of 0.03 Tesla. We know the charge because it's a singly ionized particle, right? Positive particle, which means it has a Q of 1.6 times 10 to the minus 19 coulombs. And we also know the radius of curvature, because if this distance here, from here to here, is given as 0.8 meters, this distance here is d is equal to 0.8 meters, then the radius of the curvature has to be 1/2 of that, right? D over 2. So that would be 0.04 meters. So the only thing that we do not know is the velocity. But we do have an equation that tells us the velocity of the particle that will make it through the first portion of the apparatus, undeflected, so that it passes through this opening right here. Right. So velocity is equal to E over B in, right? And we are given the E field, because that is 2 kilovolts per meter, and we're also given the input magnetic field. We can therefore get a number for the velocity, or more preferably, we can plug this equation into the previous equation to get an analytical solution for the mass in terms of all the known variables. So we'll do that. We'll write that the mass is then equal to, we have the radius of curvature times the magnitude of the charge times the magnitude of the B field in the detector region, and then we're going to divide that by E over B in. So this is the electric field down here, and because it's in the bottom of a denominator, it pops up top, and we have the magnitude of the input magnetic field up top, right, which we can then plug in numbers. That gives us, we have a radius of, as we said, the radius is half the distance from the hole to the detector where it hits, so that gives us 0.04 meters. We have the charge as 1.6 times 10 to the minus 19 coulombs. B naught is given as 0.03 Tesla. The input magnetic field is 0.05 Tesla. And that will all be taken over the electric field strength, which is given to be 2 kilovolts per meter, which we will write as 2,000 volts per meter. We plug all that in to a calculator, and we get a final result of 4.8 times 10 to the minus 26 kilograms. And that's our final answer.